Okay, on the Unit 3 review for the definitions, be sure whenever you're filling those out that you skip lines in between definitions, you underline the term, and you number them as you go. The definitions will be due the day that you take your test. The first part of your test will be matching. You'll have 13 terms, 13 definitions that will need to be matched up, so you need to be very familiar with these words and what they mean. But to know the location of your metals and nonmetals, you have your staircase that separates those on the periodic table. Your nonmetals are to the right. Your metals are to the left. If you ever forget, just look at what elements are on each side there. There is one exception. Hydrogen in the top left-hand corner, of course, is going to be a nonmetal. STP stands for standard temperature and pressure, and you need to be familiar both with what it represents and those values for each of those. So standard temperature is going to be 0 degrees Celsius or 273 Kelvin. And standard pressure is going to be 1 atmosphere, which is also equivalent to 760 millimeters of mercury or 760 torr. So these values are also correct for those. Molar volume at STP, if you have 1 mole of a gas at STP, then that's going to be equivalent to 22.4 liters whenever you're talking about the volume of that gas. But it has to be at STP. And then to calculate density of a gas, remember our basic formula for density is mass over volume. So our density of a gas will be molar mass divided by molar volume, where molar mass is something that you get from the periodic table. You just find the atomic mass values and then you add them all up for the elements involved. And then your molar volume is what we just wrote before. It's always 22.4. So this top one's grams per mole. The bottom one is liters per mole. So your mole part will cancel and your units would be grams per liter for that density value. And we'll work a problem on the back where we're going to use that. For number 1, we want to find the molar mass for aluminum hydroxide. So we're going to have 1 aluminum. We're going to have 3 oxygens. That 3 is distributed through everything in the parentheses. 3 hydrogens. So we go to our periodic table, find out how much each one of those weighs. Aluminum's 26.98. Remember, we're rounding those to 2 places after the decimal. Oxygen is 16.00, and hydrogen will be 1.01. You add those values together and you get 78.01 grams per mole. Remember, if it ends up being a whole number, you still have to write it out to the hundredths. It would be 0.00 at the end. How many moles are in 450 grams of barium sulfite? So we're going to start with our value that's given in the problem using your units and the substance. We'll put it over 1. And then to go from grams to moles, we need to find our table grams, our molar mass from our periodic table. So barium is 137.33. You add a sulfur, 32.07. And then 3 times 16 for the oxygens. And we add all of those up, and you get 217.40 grams per mole. With barium sulfite for each of them. Make sure your units cancel. We have grams and grams, so we'll be left with our moles. Remember, of our numbers on the bottom here, that means we're going to be dividing. So I have 450 divided by 217.40. We need 4 significant digits because we have 4 in that one. This one down here has 5. So we go with the least. We'll go with 4. We'll put it in scientific notation. Times 10 to the 0. And then, of course, we get our units from right here. Moles of BaSO3, barium sulfite. Put a box around your final answer. We're starting out with plutonium atoms, and we want to find out how many moles that would be. And you need to think about what is plutonium. Plutonium is an element. So when we talk about the particles that make it up, of course, it's atoms, and a mole of plutonium would have 6.02 times 10 to the 23 atoms in it, using that Avogadro's number. So we're going to start with the number given in the problem that we underlined, atoms of plutonium over 1. And then we're going to use Avogadro's number. And since atoms is on top, we need to put our 6.02 times 10 to the 23 atoms on the bottom. And that's equivalent to 1 mole of plutonium. Our atoms will cancel. We'll be left with moles of plutonium. And again, since this value is on the bottom here, we're going to divide. And if you're using Miss Reasoner's calculators, we have to put this value in parentheses when you divide. If you do not put anything that's in scientific notation in parentheses when you're dividing by it, you will get the wrong exponent. So when you type that in, you should end up with 3 significant digits from the 3.25 and 6.02. They both have 3 sig figs. So we'll have 5.40 times 10 to the negative third moles of plutonium. Number 4, we're starting with 1,200 grams of acetic acid, CH3COOH, and we want to find out how many atoms of oxygen there are. So we're going to start with our 1,200 grams of CH3COOH over 1. And when you're in grams, there's only one conversion we can use. That's the table grams or molar mass. So if you have 2 carbons, 4 hydrogens, and 2 oxygens that we add up, we get 60.06 grams. Again, just going to the periodic table for each one of those values. That will be 1 mole. Once you're in moles, we can go to the particles. And you have to think about what kind of substance CH3COOH is. It's made up of carbon, hydrogen, and oxygen. They're all non-metals, and so that would be a molecular compound. So whenever you have 1 mole of a molecular compound, those particles that it's made up of will be called molecules. So we're going to have Avogadro's number worth of molecules of CH3COOH. So we're almost done. We have one more conversion. If you have just one single molecule of acetic acid, look at the formula for it, CH3COOH. How many of those atoms are oxygen? There's 2 of them. So we'll have 2 atoms of oxygen for every single molecule of it. Make sure your units cancel. We've got grams, grams, moles, moles, molecules, molecules, and we'll be left with atoms of oxygen. When you go to type this into your calculator, we're going to start with our 1,200 grams. We'll divide by our 60.06. We're going to multiply by the 6.02 times 10 to the 23rd, and we're going to multiply times 2. If it's on top of the line, you multiply. If it's below the line, you divide by it. So we started with 2 significant figures in our problem, and there were not any others that we worked with that would be smaller than that. Remember, if you have a whole number like our 2 here, we don't look at that. It has an infinite level of significance. So, rounded to 2 places, we get 2.4 times 10 to the 25th atoms of oxygen. Do not forget to look down at the bottom, or not the bottom, but to the far right of your screen when you type it into the calculator. When you're rounding off, you don't need to forget the times 10 to the 25th at the end. And if you think about it, if you had 1,200 grams of it, you wouldn't have 2.4 atoms. You should have a really big number that you get, which we do. Okay, number 5, what would be the volume? So that means that we're looking for liters of 2.25 grams of NO2. So we're going to start with the number in the problem. And think about what's the only thing we can go to from grams. We can go from grams to moles. So in order to do that, we need to find out how much NO2 would weigh on the periodic table. You've got a nitrogen and 2 oxygens. So that's how we would calculate it. And you get 46.01 grams. And then once we have it in moles, when we want to go from moles to liters, that's when we're going to use our molar volume. If you have a mole of any gas at STP, then it would take up 22.4 liters of space. So make sure your units cancel. Grams, moles. We're going to be left with liters. So we're going to divide, and then we're going to multiply. And we rounded to 3 sig figs. The 2.25 and the 22.4 limit it to that. We get 1.10 times 10 to the 0 liters of NO2. For number 6, we want to find the density of a gas at STP. So remember, density is mass over volume. So if it's a gas here, we're looking at molar mass divided by molar volume. So our molar mass will be 11 carbons, 26 hydrogens, 1 nitrogen, 2 oxygens, a phosphorus, and a sulfur. So you have a lot of different elements there you had to add together. You end up with 267.42 grams per mole. Our molar volume is a constant value. Our per moles will cancel, so we'll be left with grams per liter. So we go and divide those, round it to 3 sig figs. We get 1.19 times 10 to the first grams per liter of C11H26 NO2PS. For percent composition, remember we need to do part over total times 100. So we're going to list all of our parts. We have 4 different elements here, so we'll have Na, H, C, and O. And we're going to list how many we have of each. So we have 1 of all of them except for oxygen, we're going to have 3. And then we're going to need to multiply by our molar mass values from our periodic table. And all of them are going to stay the same except for oxygen. Whoop. We're going to have 16 multiplied by 3. So that's going to give us 48 for that one. But the other 3 will remain the same. So those are all of our individual parts. And then we need to get a total. So we're going to add all of those up. And we get 84.01 as our total. So you're going to take each one of your parts here, divide by our total, times 100. And we're going to get 4 different answers. And remember, whenever you divide these and multiply by 100, you'll end up rounding your answer to 2 places after the decimal, to the hundredths place, just like we do molar mass or money. So we're going to take 22.99, divide it by 84.01, multiply times 100, and whenever you round it to 2 places after the decimal, we get 27.37% of sodium, Na. And you're going to take 1.01, divide it by your total, times 100, we get 1.20% hydrogen. Take 12.01, divided by your total, times 100, we get 14.30% carbon. And then finally, 48 divided by your total times 100 gives us a percentage of 57.14% oxygen. A way to double check your work at the end is to add up all of these percentages. They should be very close to 100%. You'll notice when you add this one up, you should end up with 100.01. That's okay as long as it's very close, because of rounding sometimes we'll be off just a tad. So that's good to go. Okay, how many grams of silver are in 5,000 grams of silver sulfide? So to find a percent, partial over total times 100. So our part that we're dealing here is the silver. So the silver is Ag2, and our total is Ag2S. So we look up silver on the periodic table, it weighs 107.87. And so then on the bottom, we'll have the same, only we're going to add to it a sulfur. So whenever you type that in, again, we'll round it to 2 places after the decimal. We're going to get 87.06% silver. So this is kind of an in-between answer. We're going to use this to help us figure out exactly how many grams of silver were in a 5,000 gram sample of the silver sulfide. So we have to change our percent back to a decimal. That kind of undoes that multiplying by 100. We move our decimal back 2 places. We get 0.8706. We're going to multiply that times the mass that we were given in the problem. We're starting with a 5,000.0 gram sample. And so that percentage of 5,000 will just be silver, and it works out being 4.353 times 10 to the third grams of silver. We're rounding it to 4 sig figs because the number in the problem was given as 5, and then whenever we were adding, when we found our percentage, that was only 4. So when you look at those two choices, 4 will be the limiting number of sig figs. When we're given the percent composition already and we want to work backwards to find our empirical formula for the compound, remember we're going to just assume a 100 gram sample, and each of our percentages we can just kind of rewrite as grams of that substance. So we're going to have carbon, hydrogen, and oxygen, and we're going to say carbon we have 39.99 grams, hydrogen will be 6.72 grams, and then we'll have 53.2 grams of oxygen. Remember, we can't really compare grams of different elements. We need to get them into the mole unit in order to compare them. So we're going to divide each of our grams by the molar mass for that element. That will change it into moles for us. Whenever we divide here, the gram units will cancel out. And we'll write out about 3 or 4 digits past the decimal. We don't want to round it off too much. And then once you have all of these, you're going to look for the smallest. So out of these 3 values, the smallest one is the last one. And we want to divide all of these by that number. And if you want to make yourself a little reminder, this is the smallest one we're dividing by. So whenever you do that, the mole unit goes away entirely. We're just getting a ratio between these different elements. So the bottom one, of course, will be 1 when you divide by itself. The top one is very, very close to being the same value. It is also 1. And whenever you divide the middle one, it is very close to being 2. So we put it together just in the order it's given. Carbon will have 1 of them. Hydrogen we have 2. Oxygen we have 1. And that is our empirical formula for that substance. If we wanted to find out the molecular formula, what it really looked like, not just the reduced form of it, remember the way that we get our ratio is to take the molecular mass, which will be given to you in the problem, and we're going to divide it by our empirical mass. And we're going to have to calculate that from our empirical formula. So our molecular mass is given to be 180 grams per mole. And if we take our empirical formula here, we have a carbon, 2 hydrogens, and an oxygen. So we'll add those together. And that gets us 30.03. So that is our empirical mass that will go on the bottom here. When you divide, it should be very, very close to a whole number, and we can already kind of see if we have 18 divided by 3, we will end up with 6. That is what you will multiply your empirical formula by. So instead of having CH2O, we're going to multiply everything across here by 6. So we're going to have C6H12O6. And we have glucose. Okay. If you have a hydrated salt with a formula of COCl2 and then some amount of water trapped in there, we're going to break this down into 2 parts. The anhydrous compound, the part that would have water removed, and then the water. And it says that together it weighs 2.105 grams. So that's all of it together. We have 1.149 grams of the cobalt chloride once the water is driven off. So we're going to have 1.149 grams here. And in order to find how many grams of water, you're going to have to take your 2.105 for the whole thing and subtract the 1.149. And so that's going to give us the amount of water, which is 0.956 grams. And then at this point, it's just an empirical formula problem. You have to divide by the molar mass. Water is 18.02 grams per mole. And then for cobalt chloride, You have a cobalt and 2 chlorines, you get 129.83 grams per mole. So whenever you divide the top, we get 0.00885 moles. When you divide the bottom, we get 0.0531 moles. So whenever you compare them and get the smallest, the top one will be the smallest. So we'll get 1. And whenever we divide the bottom, we get 6. So when we write our formula for this hydrate, we have COCl2 and then a dot. And then instead of the X right here, we're going to put our number of 6 H2O. So in that crystal lattice structure for the cobalt chloride, you're going to have 6 water molecules trapped for every single formula unit. Okay, we have potassium reacting with oxygen. So whenever it forms a compound together, we'll have these 2 elements involved. And we have 3.91 grams of the potassium to start with. And once it reacts, it yields 7.11 grams of a superoxide. So we need to take our total mass, subtract how much of it is the potassium, and that's going to leave us with the quantity of oxygen. We need to divide by the molar mass from the periodic table. You'll notice our numbers work out very nicely on this one. So we get 0.1 and 0.2. Which one is smaller? The 0.1. So when we divide, we get one of these for every 2 of those. That's not a 2. That's a 2. So our formula for our superoxide is KO2. Now on your test, you will not have multiple choice options on these types of problems. You will have a setup very similar to what you're seeing here on your review, where you are having to work them out, showing all of your work, following all of the steps in order to get full credit on them. So don't forget to show what units you have, cross out units, box your answer, be sure you put all of your units and the substance on your final answer. Don't be careless, be sure you're showing all of your steps. On the last page of your review, you have a checklist. We are going to turn this in on the day that we take our test along with our definitions. So you need to be sure that you've gone through and kind of assessed how are you on each of these things. I understand the concept of a mole. I can tell whether it's ionic or molecular. But maybe I'm only kind of fair at figuring out if it's atoms, molecules, or formula units. So go through, kind of assess where you're at. Anything that you mark as poor, you need to be sure that you are studying that. And then fair will be your next ones you study. And then the last thing you might look at before you take the test is the ones that you feel fairly confident about. But the most amount of time that you'll need to spend will be those that you kind of identify that you have poor kind of knowledge of. Finally, you need to predict what your grade will be on the test. It needs to be just a single numerical grade. So maybe you think that you've got it mostly down, but there's just a little bit you're not so sure about, and maybe you think you'll have a 94. Okay, just whatever grade you feel like you might earn, you'll record that there, and we'll turn this in when we take our test.